Thank you for joining us this afternoon. Welcome to Rosenblatt's 5th Annual Tech Conference, The Age of AI. My name is Kevin Cassidy. I'm a semiconductor analyst at Rosenblatt, and it's my pleasure to introduce Dr. Laura Mirkarmi. She's the Senior VP and Head of Semiconductor Engineering at Adeia. Dr. Laura leads the 3D technology team at Adeia and focuses on hybrid bonding, advanced packages, and thermal management technologies for future generations of electronic products. She holds over 100 patents and has 60 technical publications. She earned her PhD in material science at Northwestern University and a BS in ceramic science and engineering at Pennsylvania State University. And I will add that Adeia won the Most Innovative Technology Award at the Future of Memory, the FMS 2025 conference. That was just held a few weeks ago. So congratulations, Laura, on that. And today we're going to talk about hybrid bonding, and then also we'll go into Adeia's latest invention, rapid cool, or what I consider as chip scale liquid cooling. Two very important topics. But maybe I'll start off with asking Laura if she could just give an overview of Adeia and how you got into the semiconductor market.
Sure. Thank you so much for the introduction. So what I'd like to just do is just to get everyone oriented around what Adeia's product is. And our product really is intellectual property. We license patents, and we have revolutionary innovations in both media and semiconductors. We have over 35 years of history, which is sometimes people aren't easily aware of that because our name has changed a few times. But our history is in pioneering innovation and also licensing success. We have greater than 13,000 patents in key technology areas that are relevant to our greater than 115 customers. And finally, in 2024, our revenue was $376 million. Now, I'm a technologist, and I'm going to talk about some of the technology in the semiconductor area, but we thought this was a good overview on the company.
Yeah, thank you for that. And yeah, if we will start to go into the hybrid bonding technology. Now, this is a technology that is growing quickly within semiconductors, and I think it's necessary if a company wants to get to the chiplets. But I'll ask Laura to go into the background of hybrid bonding and why it's so significant, especially in my view, with Moore's Law slowing down. At least the economics of Moore's Law is getting prohibitive. So I'll just ask Laura to give a few slides on the hybrid bonding, and we'll be open for questions. And I'll also have other questions for Laura. Thank you.
Great. Thank you, Kevin. Yes, Kevin was interested in me talking just a little bit, giving a sort of high-level tutorial on the chiplets. So we're going to start out there, and then we're going to move to talk about the hybrid bonding technology and why it's relevant here in the chiplet space. So I like to think of chiplets as just very simply, it's really taking a part of a function that exists in a monolithic chip that is shown here in the left figure and pulling that out into the first evolution of chiplet design was to pull out an entire function and put it in a chip. So you'd have a multi-chip package. And some of the functions that you could pull out and separate are things like the memory or the processor, right? And the other thing that happens when you do that is then you need to have your I/O blocks that are communicating between these two important functions, for example, in a high-performance compute modules. But the holy grail and the vision that exists out there for the industry is to really move to this concept that is shown in a very simple schematic, where sub-functions within this, for example, processor block, or either a central processor unit or a graphics processor block would be pulled out. And the motivation behind doing something like this is that it can enable significant cost savings while achieving performance enhancement. In the semiconductor industry, it's somewhat of a conservative industry. If they're going to adopt something, they want to reap the reward. And so performance is usually what's driving the new technology adoption. What's interesting with this technology, and we're going to talk about that a little more in the second slide, is why you get high value in hybrid bonding. But just by separating out, for example, everything, pulling it out from a monolithic chip, which takes 3 to 4 years to develop, you can actually reduce your development time and bring new products into the market by, in 2 to 3 years. What can happen with this chiplet level SoC is that we would be designing, or the chip architects would be designing, subsets of functions, and those could be using sometimes legacy nodes, which aren't the most expensive. And maybe if you're using a legacy node in a processor, you might be then instead adding your latest, greatest memory or your latest, greatest I/O bus that can allow very, very high bandwidth communication between your processor block and your memory block. In this case, what I show with this true chiplet architecture, the green is on top of red, and here red is representing local memory. So this concept of being able to bring development cycle times down to about 1 year is significant for companies to be able to bring out products that are optimized for the specific application. In addition to that, once you separate out some of the processes, like process for an XPU, a GPU, or a CPU from memory, you actually can reduce your overall cost, because no longer are you sort of held by the cost of the high-end latest transistor node per silicon. You now can make this chip much smaller. The other thing that happens is that these monolithic chips have become huge over the past 10, 15 years. And what that means is that your yield is very low. So you start to have cost hits in that particular area, making a new product introduction very expensive. So what you can see here is that the idea, since you are testing and verifying at the die IP or at the chiplet IP, you significantly can reduce your numbers of bugs. You actually are using only known good die, and you can reduce your overall costs, while the industry has shown that you can actually have significant improvement over, for example, a legacy node moves to the latest transistor. And what AMD was showing is how the performance in actually going to a chiplet architecture was actually yielding the equivalent performance by disaggregating chips to that of using the advanced node. One thing for this group to think about is the fact that the latest transistor nodes, not only are they slowing down, as Kevin mentioned, but they're extremely costly. So if you're not really getting that benefit out of using that expensive technology, the industry will absolutely move to an area where they get the same performance and at a lower cost in this advanced packaging platform.
And Laura, if I could ask about that, just a couple of points. That when you mentioned different process nodes, which would be interesting, analog maybe doesn't scale as well. Can they also come from different foundries and then put into a package, or does all this happen at the foundry level?
The unique feature is that they can come from totally different foundries. So it's really the hope is that some of the smaller players, it would lower the bar to get involved in building a system on chip. So it's a very good question, because by leveraging things so that they can be procured, some companies have they're vertically integrated on the memory, maybe not on the processor side. And so we're seeing a lot more collaboration, and the supply chain is using multiple vendors to achieve these system on chip architectures.
Okay, great. Thank you.
Thanks for the question. So I'm going to move on to talk a little bit about why the interconnect matters. So in this slide, I have a schematic on the left, which is a microbump, which is sort of I'd say it's the largest interconnect that's used out there in packages today. It is the incumbent technology. And this technology can be done with either mass reflow or thermocompression bonding. And this technology has brought about a lot of excellent innovation, but there are some limitations, the limitations primarily being pitch scaling. The other limitation is that there's a very large standoff between the two die, making this interconnect actually quite large. And we'll get into a little bit of the reason why these features, this is a challenge. Number one, the industry is building these high-performance compute modules, which require very large bandwidth. So you need to have many, many IOs, because there's a lot of processing that's going on in parallel. So this limits the ability to scale those interfaces. However, we like to say that hybrid bonding is a great example of when less is more. There is much less in terms of processing after the wafer is fabricated, because there's now no underbump metallurgy. You see these layers have been removed. There's no underfill in between the two die. There is no standoff. There isn't this very large offset, so things can be integrated and brought closer together. There's no heat during the bond, which for heterogeneous integration is really, really useful. The hybrid bond technology allows you to attach a die, and what you do that at room temperature, and the dielectric bond happens spontaneously. So you immediately get the alignment that you have, and you can then consider building many types of heterogeneous types of die. One die, maybe your sensor die or your memory die, is very sensitive to temperature. It can only withstand 175 to 200 degrees C, whereas your processor die can be processed at much higher temperatures. So it allows the industry to consider new ways of integrating parts in a more flexible supply chain. And when I say why less is more, well, you get more interconnects per millimeter squared, a factor of 10,000 more. The other thing that is important to note is you now have scalability. And what scalability does for us is it allows us to have this enhanced thermal performance. With this very small interconnect, we have a very low LOCR. And with that low inductance, capacitance, and resistance, we can have very low power interfaces now communicating between these chips. And really, as we're building these structures for more processing, we really want to reduce the power it takes to get the same number of computational flips, so to speak, in the language of computer science. So the other thing that's important is that these numbers I'm showing are taken both from our own paper, which is cited here. This is back quite some time ago in both 2017 and then again in 2021 that talk about the performance enhancements, but it's also been noted by some of our licensees, most notably Kioxia and Western Digital. They talk about the importance of this power reduction of the interfaces. The other thing is we now have an area reduction, an overall reduction of the module itself. And we now have this interconnect that performs as if it had been built monolithically. So it's got very low standoff, zero standoff, high thermal performance, very fast electrical interconnect as well. And it's just extremely efficient for high performance compute.
Yeah, that number, a million IOs, is staggering to me. And, that's super important for, as you're doing parallel processing, that GPUs are using and why they need high bandwidth memory. So I imagine you're going to talk a little more about that, but.
Sure, I can just mention here that just think about that this is this calculation is for 1 micron pitch interconnect. Right now, there was a huge leap in the first product that came out that was in die-to-wafer form between microbump and hybrid bonding, and they are operating at a 9 micron pitch. But what's interesting is that was significant because this technology, the microbump, can't get there. We see that the industry is moving to continue to push that down further. And I can also say that in the wafer-to-wafer hybrid bonded products that are out there, they are already below the 1 micron pitch. So in those cases, they are looking for this type of very, very high bandwidth. And some of these numbers about the power reduction become extremely important when you have that many interconnects between your memory and your logic. Right. So I think I'll move on to this next area, and then this will be concluding the section around the hybrid bonding, and then we can take questions. And Kevin, if you have any further questions. What I wanted to do was to show the impact of this AI market, given that this technical series is talking about the AI era. It was very exciting. Earlier this year in March, I attended a packaging conference. It's called IMAPS, and your representative was Gabriela Pereira. She gave a very interesting talk. So high-end advanced packaging actually surpasses automotive now in 2025. So that was significant. Automotive has always been sort of the largest growing market in electronic packaging, but what's happening is this incredible market requirements and pull for more computation, more data servers is what's driving this. And some of the data that she shared is that over the next 5 years, we can expect to see 29% increase in AI accelerators. So the total market is going to move from 110 billion to 230 billion. It's a huge opportunity. The high-end advanced packaging modules themselves, they're going to experience somewhere between 11 to 33%. And this is when we start to look at what's inside that data server. So that's growing at 29%. But this is a schematic, sort of our vision of the future. And inside are the XPUs, or the processor units, that are then talking to the memory modules. So you can see that the memory modules are expected to grow at least 10 to 15% in the memory market. And the logic is growing between 30 and 40% in the next 5 years. The semi market itself has about a 6.8% CAGR. And so what we think is important, and we're really excited, is that it really is this high end now. Oftentimes the new technology, which brings additional performance, it starts off kind of with a trickle. But you can see that the growth is explosive. we're very excited because hybrid bonding is being adopted into many different segments, especially in the memory and logic because of the reasons that I explained earlier. But specifically, just to explain to this group of people, why is it moving? Why are we moving to hybrid bonding? A couple of things. So the large language models, they're extremely power hungry. And again, I talked about the need for efficient interfaces. And the best way to do that is with hybrid bonding. The bottleneck is always the access to the memory. So a couple of things there. Again, high bandwidth, fine pitch. Again, this is hybrid bonding. More importantly, the thermal performance of a multi-die stack in the high bandwidth memory devices is really critical. The industry would like to have 16 die stacks. However, with a microbump at 16 high, the temperature performance is not very good. In fact, they will heat up so much that you start to lose performance. So that is why you see the memory manufacturers talking about when they will be bringing out a hybrid bonded HBM part. It's primarily because that's when they're going to make that transition to the 16 high die stacks. And then finally, one of the other trends that's important to note, in my image that we've created here, which shows the memory have up to eight die stacks, everything here, even to the interposer, we envision will have hybrid bond interconnect in it. It will become pervasive. What's interesting is that the silicon interposers are becoming so large because of these large language modules and the need to have the compute and the memory very close to one another, that they're trying to figure out how to deal with the silicon interposer, which causes a lot of warpage. And it looks like the one solution is using bridge die. But all these bridge die, I believe, will be hybrid bonded so that you can achieve these very high performance interconnects. So that's what we see is happening, and a variety of companies have already announced that they're working on this technology. So Kevin, that concludes my section on the hybrid bonding before we get into the thermal challenges.
Okay, I'll just ask a couple more questions on that. The memory industry, you had mentioned as they get to 16 high on the DRAM side with high bandwidth memory. Is that HBM4 then, or is it 4E?
So HBM4E, I'm not sure if that's 16 or just the 12. So what we hear and understand is that these I'm not an expert in exactly what the E means, but it just means some sort of a modification of the type of performance that you can get. So I understand that in the HBM4 that they'll be doing this both in the conventional microbump and in the hybrid bonding. So it may well be the E, although sometimes these names have been changing, and that the 16 die may come out in the version after that.
Okay, and why is it that, so you had mentioned Kioxia and Western Digital as licensees now for your hybrid bonding, but the logic market seems to be a little slower. Is it there just wasn't as much demand until now to go to this?
I think it's a great question. So we don't always disclose all of our licensees because of our agreements that we have. We certainly do have some agreements with some processor companies that are building these advanced high performance compute modules, for example, and or similar types of packages. Part of it is simply that to some extent, it depends a little bit on the supply chain and where they go to bring the technology forward. So some of our customers, they license early ahead of bringing the product into the market. very early, like maybe 3 or 4 years early, and others, were after the product comes into or the technology comes into the market, then we're licensing them. So it's a little bit unclear. I must say that at first we thought that there might just be one leader, that was going to move forward in trying to move into this technology of building 2.5 3D. And typically that is done when people want to sort of leapfrog the competition and gain significant market share. And so we just weren't sure when the others would be launching in and taking up the hybrid bonding technology. So now, based on the reports that we hear out of many semiconductor companies, this is something that's actually very close. In the next 2 years, we hear people talking already this year about what they're bringing out in 2026 and 2027. So a little bit of it was, a slow start, and the first adopter, how is the quality, how is the performance of the product in the market? And now I think that those proof points are out there. The rest of the industry is trying to catch up and move forward.
That's
Did
great.
I answer your question?
Yeah, that's great. Thank you. And, it's to lead into your next topic is, now that you've solved this problem, you've got more density inside the packages. And so now there's going to be a heat problem with all the work being done inside the package. So I'll use that as the lead into your rapid cool.
Okay, thank you, Kevin. So that's exactly what we were thinking several years ago. We started looking into, well, now if the industry is going to have this technology, this interconnect that allows you to stack 12 or 16 or 20 die stacks in the near term, the thermal issues are going to start to become a bigger problem. And then also, how do we get the heat out of, for example, logic applications, right? Well, because the industry has been talking about this since 2020. And what I show here on the left, the two main trends that are happening, which I think are why we need to have a revolution in the hardware based in this AI era that we're moving into. The power density is shown here as a function of year, and this is showing how it used to be that if you were designing a silicon IC, your processor needed to have a certain power density, and if it started to creep up too much, sometimes you even have to bring it back down in the next year, the next product. Well, that's all been thrown out the window now since the AI era is here, and now the power densities predicted are extremely high in the next, say, 10 years. Yes, so these two factors, which are driving up the power and the package size, again, in order to manage these large chipsets, I explained how costs can also become exorbitant. So there's this push to move to hybrid bonding, which does help with managing the power in the package. But what we think is that we need something more than that based on this doubling and tripling the power density here. So the solution is many companies, there's many emerging concepts out there for how to cool these modules, how to cool things at the data center, and then also how do we cool them more efficiently? Because the cost of cooling things can also be exorbitant. So Rapid Cool is our trademark for our drop-in replacement of a liquid cooling. And again, it's a direct-to-chip liquid cooling technology. And I'm going to talk a little more about what that is and why we think ours is unique and will be utilized in the future. I should mention that we announced this at the conference, the iTherm ECTC, in late May. So our paper is cited here if you want to read that paper that goes into a lot more details about the performance of the technology. But what I did for this talk is just pull one example to kind of show how this is improved over conventional TIM-based. TIM is a thermal interface material with a cold plate. And the conventional approach is that you have this copper cold plate with this thermal interface material. And so what we did in our own lab is we built up our own test structures. And what we did is we take these heater chips and we attached two different types of cold plates. One was a gaming cold plate, and another was what we would call a high-performance compute cold plate. So something you would see in a data center, for example. And both of these use a slightly different TIM because of the application space there. And this is using the very common TIM. And then there's the Adeia, our ICS, our integrated cooling solution, -5 is just its number. And so with this particular design, which isn't our most optimal, you can see that for the same temperature, let's say the temperature requirement needs to be 100, you can see that our cooling solution allowed us to drive the power on the chip up to 700 watts compared to the gaming cold plate, which was 250, and the high performance, which was 400. So this is a significant improvement, and it's about 3x improvement over the cold plate for the gaming situation. And then we've done additional testing, which I'm not showing here. Basically, we can customize our cold plate for the need for the power in that particular chip. And what we found is in our optimal design, we can get an additional 20% lower resistance, which brings us up to 3x improvement over the HPC or the high performance cold plate. So right now, where we are with this technology is we still consider this to be early. And here at Adeia, what we do is we often want to work with our potential customers to know that our technology will perform in the application of their interest. And so we are at the stage where we're working with some customers who are evaluating our technology for their roadmaps, which are similar to what I've shown in terms of the power densities required in the chipsets over the next few years. So this is kind of a final slide, and you might have seen this if you listened to our earnings report. And this just shows that really we think that the first adoption of this technology, again, will be at the high end in the data center where it's needed most. And these are some of the specifications that we've measured on our new cooling technology, greater than 70% less thermal resistance. So this increase by showing much lower thermal resistance, we are able to cool things about 3x times higher power density, or allow 3x higher power density to maintain the same temperature. Again, we think that the custom design is something that will really be attractive for the industry. And because of the large size of packages and the direction that the industry is going, we think that this technology will significantly better reliability over any type of a cooling solution with a metal tin or the phase change material tin. And so that concludes my portion of the slides.
Great. Thank you. And, just to understand that rapid cool, that would be implemented, again, it's hybrid bonding to put that onto the certain portion of the silicon?
Yes, so there is right now, it could be either what we call direct bonded, but silicon to silicon bonding with or without any metal. And we envision that the first iteration would not have metal in between. And so what's unique about it is that by removing that tin, we remove most of that thermal resistance, which is fundamentally stopping the flow of heat to come out of the hot chips. And then by us looking at and designing sort of improvements around what gives you the best thermal performance, what gives you the best pressure drop, meaning lowest pressure drop, but still achieving the thermal performance, we found that this technology looks like it can be a drop-in replacement, which is, you need to have that for the ease of adoption and the industry moving forward to bring it into products.
Yeah, that's and so I guess as a drop-in replacement, are you saying that even in the data center, you could pull out your ones that didn't have the liquid or a rapid cool on it, and you could put in a shelf that would have it?
You could take out the whole package. Yes. You could just take out that module. And we want to, it needs to have the same simple connectivity to the cooling, whatever the cooling lines are, whatever connectors. I mean, in our tests, we're also testing everything with whatever standard for our customer, for example, in terms of connectivity to test. And of course, this is still early, right? This isn't a product yet, but this is technology which we think can help the industry move forward and meet some of these high thermal, these very high processing and very hot situations in a very different approach. So, right now it's like a little bit of a argument between IC designers and the thermal and assembly and system designers. Yeah. The system and thermal designers are very frustrated because they have this big problem to deal with. So hopefully this idea is that these guys can come together early on and even understand with a simulation of how will this perform in the product and make it hopefully more smooth in terms of bringing product to the market.
Yeah, I think as we're seeing all these GPUs are going up to 1,000 watts with just a single GPU. This is a creative solution to the problem. And we only have 5 minutes left, and I'm open for questions from the audience. But this next question might take an hour to discuss. But right now you're saying obviously the GPU, or even in the data center in general, probably CPUs even need this. But what about when we get out to the network edge, if more and more inference stage AI moves to the network edge where you don't even have fans or liquid cooling possibilities, you're more remote. Can that work in that application also?
I believe so. What's interesting is that when we first started looking at it, we looked at the gaming environment, which is much less aggressive in terms of thermal challenges. And what we found is that we could have very, very low flow rates, so it could be very efficient. So efficiency goes a long way in thermal performance. So will it be like hybrid bonding where you adopt it at the most aggressive situation and then you start to see it filter back into other applications? I think so. I think with cooling, it just depends on what the need is and what is the best solution. So that really is more of a system optimization, but we are excited. Certainly, I can envision that there would be some compute at the edge that would still benefit from some of the concepts in the technology we've developed here.
Okay, great. Yeah, it's this is exactly what the Adeia's charter is to look around the corner and come up with new ideas before the industry knows they need it.
Well, and I always say we are very fortunate in that we get to talk to our customers, find out what their problems are, also pay attention to what's going on. And because we're not building product, we have that luxury of being able to look ahead. And the reason that we do it is we want to bring value to our licensees so that they keep coming back and relicensing our portfolio. So we must really consider that we are continuing to drive value in their technology and their roadmap. That's our goal.
Great. Well, congratulations. It looks like a great product.
Well, we hope it will become a product soon, and it is a great technology. Thank you. Yeah.
All right. Yeah, thank you for joining us.